Okay. Okay, hello, welcome to the second day of the conference during the workshop. Sorry for the delay. We were trying to solve the technical audio problems that we have discovered. Hopefully, we don't have that noise today. Okay. Um, so we start this morning with Gonzalo's course from the content of thermodynamics. So, Gonzalo, can you get your so, I would like to hear some of the rest of the maybe one book, I also actually anyway, I will try to give you the knowledge. Okay. Um, I think yesterday that I will give you first the part of the equation theorem and then the part of the quantum mechanics, but I decided to change the order. So that this one we will see the part of quantum mechanics. So that I prefer this presentation, but I will also at some point speak to the blackboard and also make some calculations. So uh, okay, so let me just start. So here you can see in the left part of the net, the review, so this is the physical model about the equation and the level of actually and those are equations that large number of the material as the situation medium so that you can apply it to the frame of the practical right. The other hand, you can create this is not now, but you will see. It's not soon. Okay. Don't worry. Hola. Em,
Disculpen a los que están en Zoom que tenemos un problema. ¿Nos escuchan mejor ahí? Sí. Sí. Hola, ¿me oyen? Hola. Okay, perfect. Okay, so in the right part, you can see a 31st century engine. In, so it is a electronic system in the between the micro and nano scale. And in this kind of devices, of course, fluctuations become very important. And, and in order to describe the operation of these engines, you need to apply either a stochastic or quantum thermodynamics. One of the points, of course, of these small engines is the possibility that you might have some quantum mechanical enhancement, in contrast to the macroscopic. So, so let me just say that so that the first models of quantum heat engines were introduced already in the 60s. So there is a very famous work by Scoville and Dubois, a physical regulator, in which they propose to see the three-level measures that were being developed in quantum optics at that time as heat engines. For example, it will be like that thing in which you can see the three-level system, which is coupled with two reservoirs, cold reservoir, hot reservoir, using some frequency filters so that you can build an engine that can even reach Carnot efficiency. Since then, there has been a lot of models that have been proposed and of different types of machines, refrigerators, heat pumps, also engines. And you can more or less think about two classes of them. One of them which are like cyclic engines, and another which is engines that function in a continuous operation mode. So for the first class, they have been developed like the quantum Carnot, quantum Otto, and quantum Stirling cycles. Here you can see some of them in this paper here. And on the other hand, for the continuous operation engines, are engines that work in steady state conditions, in a non-equilibrium steady state. And some examples are lasers, masers, are these pioneering people proposed, but also solar cells, molecular devices, etc. So here you can find a review about engines in a continuous operation mode. So, okay, so why was interesting to develop and study all these models of quantum heat engines? So there are many reasons. Three of them are those ones. So in first place is because they provide us like simple setups where we can explore some fundamental issues in quantum thermodynamics, like the matter of work or heat, and we can play with them in an easy way. Another reason is that there was some interest in this question. Is there any miniaturization limit for heat engines or refrigerator? And there have been some papers that address that question, in which they propose models of heat engines that are just comprised by 2 qubits or a single qubit. Of course, one of the most important reasons is the third one, which is this question: is there any systematic quantum thermodynamic advantage in the performance with respect to classical engines? Can we profit from quantum effects in order to improve the performance of the engines? So, but not only these questions that are more from a fundamental perspective, but also because many of these models can be implemented also in the laboratory. So indeed, in the last year, there have been some first prototypes of quantum heat engines. Here I just put 4 of them, but there are more. So in the first one, in the top left, we can see what was called a single atom heat engine, in which they trap an ion, this is an ion trap, in which there is a calcium ion, if I remember well, inside the trap, and they are able to implement a cyclic engine inside this setup by using like electric noise acting as a hot reservoir, and also laser to do laser cooling in order to simulate the cold reservoir. And what we will see this example a little bit more detail later. You can see also the implementation of a quantum and social refrigerator, also with trap ion in this paper here. There has been also work on implementing cycles in nuclear magnetic resonance setup, like this one, in which you can implement an auto cycle with a spin at 1/2 particles. And also there has been implemented some continuous engines, like for example, in this platform with battery centers in diode. So, okay, so let's now go a little bit in more detail to the case of cyclic engines. And I just choose one of the examples in order to show you a little bit the flavor of this. And I choose the one which is simpler, which is the quantum Otto cycle. Okay. The Otto cycle, of course, is was introduced in classical thermodynamics. Is the cycle that the combustion engines use. For example, for the cars, gasoline. But there is a quantum inverse. In this, what we have is that the quantum system, which we call working substance, is both driven by some external agent that in general change the frequency of our system, and then we selectively put it in contact with one or other thermal reservoir that are different temperatures in a cyclic way. Okay, so this is the diagram of the cycle. We have 4 points, A, B, C, D, and 4 spokes, which are these lines that are between the points. So this cycle, in the y-axis, you can see mean energy, is the of the system, and in the x-axis, you can see the frequency. So, for example, we can take as a working substance the molecule. So this will be the Hamiltonian, and what we will do is to change the frequency between two values, only one and only. So in the first stroke that goes from A to B, we have an adiabatic expansion. This just means that we drive our harmonic oscillator in an adiabatic way from A to B. So it's an expansion because we are increasing it. Then we have and this happens like the text from the reservoir. So here we start in front with the full reservoir, we detach from the reservoir, and then we drive the system in this adiabatic mode. Then when we reach point B, what we do is to just fix the frequency and put in contact with the whole reservoir. So this produces a relaxation of our system from point B to point C. Then we go to perform another, we detach from the reservoir again, and we perform another adiabatic compression, in which we reduce the frequency up to this point. After that, we just put in contact with the cold reservoir and let our harmonic oscillator relax. And it relaxes back to equilibrium, which is point 3. So let me just go to put in some more details what happens when we do that. So the idea, so why this cycle is so simple is because indeed we are detaching from the reservoir in this stroke and this stroke, so that every change in energy will A to B will be just work, while also for the stroke from C to D, because we are just driving the system, but it takes from the reservoir, while in the stroke from B to C, we are not driving the system, so work is still, all the changes in energy of our working substance are due to exchange of heat with the rest. This simplifies a lot of things. So let me just perform some more detailed calculations about this. Is there some eraser? Ah, ah. Yeah. Okay, so the idea is that point A, we start in equilibrium with the cold bath. So the density operator of our system is this thermal state, which beta 1 is just like 1 over the temperature of the bath 1, in this case, the cold one. So H1 will be just the Newtonian of the moment oscillator for frequency over 1. So that the mean energy in this point will be just H bar omega 1 N1, being N1 the thermal occupation given by our system. Right? So then, as I said before, we did now detach from this reservoir and we drive the system. So and then we go from A to B, so that we go from state rho A to state rho B, which will be just the result of applying a unitary operation of our system, so that it is adiabatic, and that means that it's sufficiently slow so that the population of every agent state of the system remains the same. Essentially, what we are doing is that we are separating the levels, but the population of each level remains the same. So this means that at the end of this stroke, when we reach omega 2, we will have a state that looks like this. We will have this part. And we will have here the beam, where the beam. Now H2 is just H bar omega 2 omega A, and the average energy of this state B will be just the frequency 2, but it's still the population 1, because we did this adiabatic thing, no? The populations are as before. So that in this stroke, you can calculate what is the work. For this, I will put this W is the work that the external agent performs over the system in order to do the transformation. And you can just calculate by the average, what would be the standard technique? The average energy at point B minus the average energy at point A. And this is just about omega 3 minus omega 1. So as you can see, if omega 2 is greater than omega 1, this is possible. Means that we need to work in order to do this temperature. Yeah, so this is what, sorry, this is the compression. Okay. and 8 since there. Within the complexity. Okay, so another point here, perhaps a comment, is that this is the minimum work in order to perform this transformation. And why is that? It's because we reach here a Gibbs state. So Gibbs state, sorry, it's the minimum work that we perform with unitary evolution. And this you can see because this is a Gibbs state, and the Gibbs state minimizes the energy for a fixed entropy, right? Since the transformation is unitary, the entropy is fixed from the beginning. So if we reach a Gibbs state with the new Hamiltonian H2, we are sure that this is the minimum. The transformation, this adiabatic thing is a transformation that performs the minimum amount of work. Yep. Yes.
Even though that's working because these
Can you speak louder?
Yeah, I'm thinking about the noble theorem of work.
Yeah.
So this here you're identifying work already as the average change in the internal energy of the system.
Yeah.
Do you expect to recover fluctuation theorems from there?
You mean from
Does it make sense to expect fluctuation theorems in this context in the thermal machines?
Yes, I mean, this is true. This is just not the one transformation, right? So in order to derive the fluctuation theorem, you have to introduce a measurement at the beginning and at the end. But yeah, they will. So we will see in the next section how to derive the fluctuation theorem, and you will see that they apply to very general transformations. In particular, these are the transformation is one of them. Okay, so then for the second stroke, what we do is just to couple to the hot reservoir, so that it's just a relaxation. So we will go to the state Goldie. You cannot see, sorry. Thank you. So we go from state Roby to state Rosy, but Rosy is just a thermal state for the Hamiltonian H2, but we don't change the Hamiltonian here. And with the Q, it will be 1 over the temperature of the hot bath. So of course, you can model this transformation if you want. Okay, so you can even derive a Lindblad equation to describe how the system relaxes to equilibrium. But it's not so important here because what matters here is that just we are going to wait until the system is normalized. So yeah, we only meet the final state in this case. So now the average. Yeah. So the average energy at the point C after relaxation will be just H bar omega T and 2, right? Until now is the thermal occupation. This thing. Okay, so in this stroke, there is no work because we are not driving the system. There is just heat. So the heat that the system absorbs will be just H2 at point C minus H2 at point B. And using the expressions that we have calculated, we just have H bar omega 2 NT minus 2. Right? Okay, then we do the same, but for the other two strokes, okay? From C to D, we now detach again from the reservoir and perform the adiabatic, in this case, expansion, in which we go from Hamiltonian H2 to Hamiltonian H1 again. In this adiabatic manner, so that we go from state rho C to some state rho V, which is the result to apply another unitary function. And we obtain this state. We again this step will be equal to C. And perhaps we can continue for a second. Can you see if I write here? So, so in this case, we will have also some work. WCD, I call it. This is just the H1 point B minus the H2 at point C, and with that we got minus H1 omega 2 minus omega 1. So now you see that here, so we are assuming everywhere that omega 2 is greater than omega 1. So that means that here the work will be negative, meaning that we are extracting work in this stroke. Okay? Then the final stroke is just a couple from D to from D to A. We couple again to the whole reservoir and let the system relax, normalize at the temperature to 1. So we recover the initial state. Right? So that in this stroke, we also have some heat. The heat absorbed will be with H1 at point A minus H1 at point B. And this is just H bar omega 1 in 1 minus 2. Right? Okay, so now we can sum up what we get in our this cycle. So we can define the total output work in the cycle, which will be just minus the work performed in AB and the work performed in CD. Notice that now I changed the sign, but because I want to obtain what is the work out, right? The work performed by the cycle with the external apparatus. And this I can just sum up and I get W2 minus W1 into minus N. So We can also define the efficiency. Efficiency is just defined as the work output of the engine divided by the heat absorbed from the hot reservoir. So if hot reservoir was the one coupled in the stroke D to C. And if you input the expressions that we obtain, what you get is just simply that this is 1 minus omega 1 over omega 2. This is positive, right? So it is how remarkable. Well, it's only the same. It only depends on the preferences. So I can choose the frequency that I want, and I will get the efficiency that I want. But you may think, wow, but may this surpass Carnot efficiency? If I remember, you Carnot efficiency is 1 minus beta 2 over beta 1. Right? So what would you say? Well, the answer is no, of course. You can see that because it's not for all choices of these W's that we will get a heat engine, that we will get a positive work out in this cycle. In order to have W positive, we essentially need, we can see from this condition, what we need is essentially that W2, great beta 2, is equal or equal than W1 beta 1. Right? So the beta comes from this part of the thermal occupation and the W part. So what happens? Essentially, since this inequality implies that it's a less or equal than effect of the current. Okay. So indeed, it gives typical plot of the work output in this scenario. If we got W out versus W over omega 2 over omega 1, we will see something like this, where this point is this beta 1 over beta. So the work output will be positive in this region, but it will become negative in this region. So what happens in this region is that we perform positive work on the system, and what happens is that the heat flows change sign. So in that case, what we get is a refrigerator. Okay, essentially here, well, in that case, in order to extract heat from the cold reservoir, we need this input work. Okay. And the efficiency is defined in a different way.
Change the efficiency, right?
Yes.
Because I think right now what you're doing is just rescaling the spectrum of the harmonic oscillator, right? Yeah. Like switching back and forth between omega 1 and omega 2. But if I change that protocol, can I, increase the efficiency of the engine?
No, you cannot increase. I mean, so because with this adiabatic change we are performing here the less work possible, and here obtaining the highest work possible. That means that that is the best thing you can do.
So that's because you're starting with a give state and ending up with one, right?
I am, yes, this is under the constraint that the strokes are unitary, so that I am detection from the reservoir. Otherwise, the story can change.
Thanks.
So, another point is that we always see here a peak. Okay, there is a maximum peak. And this is, well, okay. So first, what we see is that in order to reach Carnot efficiency, we need to approach the point in which the work is zero. So this is this trade-off between power and efficiency. So we want to increase efficiency, the work goes down. And in the limit in which we reach Carnot efficiency, the power is zero. So many times what is interesting is not to go to this point of maximum efficiency, but go to the point of maximum power, which will be this power, and see what is the efficiency of maximum power. So, so it happens that in this cycle, so in order to obtain maximum power, we should derive the expression for the work and optimize it with respect to the frequencies and so on. But the result, so we don't have like a analytic result for that, but we can apply the high temperature limit, which will be that the beta times h bar omega are no? For j, and in that case, we can solve the problem. So, and what we obtain, so first, well, what you get is something like ratio. You have something like this. So this is plenty of exponentials. So if you want to put this to zero and solve it, no problem. I can only. But if you perform this approximation, you can do it. And the result is that the maximum power is verified at W2 over W1. So omega over omega 1 equal to the square root of theta 1 theta 2, which is kind of quite symmetrical. And yeah, in that case, the efficiency, maximum power, the high temperature limit, is this known expression, which is called like for this was derived in a different context for classical engines, but we recovered the same expression, which is something somehow not. On the other hand, what we can also do is to look at the low temperature limit. In the low temperature limit, we impose that h bar omega beta 1, h bar omega 1 is very large. And in that case, the maximum power is reached in this point, W. So omega 2 equals square root of 2 omega 1 over h bar beta 2. And then the maximum power of the density is 1 minus square root of h bar omega 1 beta 2. Okay, this was for this adiabatic approach. Of course, one can also do other things instead of this adiabatic stroke. One typical example is, because it's also easy, is what is called a sudden switch. Sudden switch will be that we just change very quickly the Hamiltonian from frequency omega 1 to omega 2, so that the system has not time to react, so that the state here will be the same as the state here, but we just change the Hamiltonian. In that case, we will report the following. So in that case, we will have this switch. And here we will have that rho V is equal to rho A, and rho D is equal to rho C. And in that case, the output work, so we can make all the calculation I did before with this case, and the output work in this case is just h bar omega 2 n2 minus some factor lambda, the alpha that I will define, plus this omega. With this alpha equal to omega 1 squared plus omega 2 squared divided by omega 1. And in this case, the heat from B to C, the heat absorbed from the hot reservoir will be just this guy here and here minus 1. So that the efficiency in this case will be 1 minus. And before we have this ratio with the frequencies, omega 1 over omega 2, but now we have here a factor, which is n1 minus alpha n2 divided by alpha n1 minus. In that case, the maximum power for the high temperature limit is the reach at this point that we omega 1. It's not the square root, but the what peak, right? Theta 1 over beta 2. And the efficiency at maximum power here. Regime is 1 minus. So let us see a little just what all this looks like. So So here you can see a plot of the efficiency at maximum power. So in the y-axis you can see the efficiency, and here you can see the ratio of the temperatures. So this is already for the choice of frequencies that maximize the power. Now what you can see is that so that will be the Carnot efficiency. This will be the efficiency at maximum power. This is high temperature limit for the batic stroke, and give it for the sudden effect. As you can see, for the diabatic stroke, you always have a higher efficiency at maximum power, and in this limit, it means like very low temperature. In principle, you can reach the Carnot efficiency, while with the sudden, you can't. So just for comparison, so a typical auto engine of gasoline fuel car is around 3.4.
This is in comparison with the classical Carnot efficiency, right? How does the Carnot efficiency looks like in the quantum case rather than for the auto engine?
This is everything quantum, but here in principle there is no quantum effect in this type, right?
So the quantum Carnot efficiency is the same as the classical Carnot efficiency?
Exactly.
Okay.
So the Carnot efficiency is just this expression is 1 minus beta 2 over beta 1. This is a problem. I mean, there is not a quantum Carnot.
Carnot cycle with a quantum system.
Yeah, but at maximum you will get the Carnot efficiency.
Okay.
If you have,
Yeah, that was my question.
so the only way to try to pass Carnot efficiency and so on, there are some works about that, but you need to have non-equilibrium reservoir. So in that case, Carnot efficiency does not apply. So it's essentially the problem. Because if you have a reservoir that can perform work over your system, then you will see like some surfaces of Carnot efficiency. But that is natural. So I mean, this also happens in classical systems. If you have, for example, a work-to-work converter, so you transfer one type of work, for example, electrical power, and another type of work, for example, mechanical work, you may reach efficiencies up to 1. It's not limited by Carnot efficiency.
Professor, maybe my question is related with the question that before. There is a similar theory in quantum regimes about the efficiency of any thermal machine is lower than the Carnot efficiency. So there is a proof of that,
Yes.
or the Carnot efficiency is just for comparison.
No, it's the proof is very similar than classical.
Okay,
You just have to take into account the second law.
okay,
So if you write down the input to production for a system, and you impose that it should be positive. And if you have like those 2 reservoirs, you can prove that Carnot efficiency can be found.
okay. But by using, of course, quantum theory.
But this is, I would say that this is more general than quantum. So it's valid for any kind of dynamics you use.
Okay.
It can be quantum.
Independent of the microscopic details.
Whenever the second law is verified, in this case, it's verified at the average level, you will get this efficiency, which is also called macroscopic efficiency, because at the end, when we have our averages, so average output work, average input heat, then another efficiency will make this.
Okay, thank you.
if you did a classical version of this where the energies were just two different energy levels, and I guess the ends were classical, it would be qualitatively the same.
So it will be quite the same. So here the only quantum part. So since the driver is adiabatic, it remains quite classical state of the system level. Because you start in a thermal state, so you don't have fluctuation of the level, no coherence. And since you go quite slowly, so you just move the energy gap between levels, but the populations remain the same, so you don't generate any coherence in any case. When it starts to be quantum, is when you don't do it. So it's between these two limits. Between these two, the unitary evolution might generate some coherence. But it has been shown that this is detrimental in general for this. So it is always better to do it like this. So in that case, the quantum effects will not help. But this is not always the case, because there are all engines in which you can prove that quantum effects may help. And we will say something.
One more question I have. So the first one, the adiabatic, you mean adiabatic in the sense of quasi-static, the process is very slow,
Yes.
slowly down, so the system is always in.
It should be quasi-static, and yeah, the idea is that the populations remain, so there are no jumps between the states during the transformation. No level.
Listen, so one thing when you talk about the power in that case, will be taking into account the time to do the cycle, which will be infinite, so the power will be zero, no? So
Yeah, you're right, but but this kind of engines or with the auto cycle, in reality, so the result is very similar. Sorry, I mean you don't need to be very slow in order to get this adiabatic or this adiabatic stroke with approximation. So it's not like in the Carnot engine, but you really need to be very slow in it. So indeed, so you see, no, you will this is 7, no? So you will be always like between these two. Okay. So this kind of cycles have been implemented experimentally in this work. So the idea is that they have this calcium ion and this linear trap with this specific geometry, it's called Tapper geometry. And the idea is that they generate some field so that depending on the actual position of the ion in the trap, so the frequency in the radial component will change. It will depend on this set. And so the idea is that they want to move the particle up and down, change and you change this radial frequency by doing that. So because in the auto cycle we want to change from one energy to the other, this is like the way they time out in order to do that. They have also some hotback, which is some electric field noise that is implemented in those electrodes there. And they also, in order to simulate the full dark, where they use a technique which is called laser cooling, to eventually input information in this beam, as you can see here, in order to cool very fast the ion. So this configuration, what it does is that it generates a force in the z direction. So that depends on the temperature. So depending on the electric noise that they input or the laser, or if they activate the laser cooling or not, you can this force changes so that you can make the particle go up or go down. And this is essentially the way they use in order to implement this autocycle. This is the theory. So, this is some simulations that we have repeated in a previous paper. So the idea is to implement the cycle that we have seen before, and where this will be the source, no? Because the pressure there in which the ion goes down, so the force points down. Then the principle with the hot reservoir implemented by the electric signal. Then when this get hot, the force change sign so that the ion goes up and the pressure and they can implement the function, and then they activate the laser cooling so that they cool down the state of the ion, and then the points down again. So this was the theory in this paper here down, and this was what they let in the spring. Looks slightly different, but still they were able to implement that cycle. Yeah. The shape is not so beautiful as this one. It's okay. And here you can see what is the position of the axis in green. So the ion makes these oscillations up and down inside the craft. And in blue, you can see the flow. So here, I don't know if you can appreciate, but this could be like red, blue, red, and blue, which is, so what they do actually in the experiment is that they have always the electric noise. So in this, in any case, active always, and then they just switch on the laser cooling at some point. So when they just have the electric noise to pass in this direction, then when they activate the laser cooling, because change time, so then the particles start to go down slowly, and so on and so forth. I don't really remember. Okay, and the idea is that doing this, you accumulate work in the movement of the ions. So the ion, in principle, will start to oscillate faster and faster. And that will be how let's say the output of the engine. But in order to get it stable, what they do is also to put another laser in the axial direction so that they generate some friction. So the ion gets some constant, so they get slower, no? Because otherwise they will kind of get unstable situation. So at the end, the work that this engine generates is dissipated, right? In this other laser that generates some friction in the set axis. So this is the working temperature of the engine, more or less. And the difference between the temperatures of the hot and cold reservoirs is just taken into account. And this is what they obtain. This is a plot of the power as a function of the difference in temperature between the two bars. So they get my power 10 to the minus 21 per second. It is approximately kBp per second at the room temperature. So it's like similar to what molecular model is, right? But the efficiency is very low. The efficiency is 0.38%. And in this case, for this cases of difference of temperatures, the economic efficiency is 2.4%, which is a very low. So just for comparison, the watch region is going to make it very much has an efficiency of 5 to 7%. So this is much less efficient, but also just because it's one of the first prototypes for the. Indeed, there has been like other or experiment in which they can improve the efficiency. In this case, they also implement the second cycle, but in this case, they have this percentage, out. So here the reservoir is also like more realistic. It's a cloud, a atom, not anymore like just the electric field or so on. And I will not enter into the details, but essentially we use a magnetic field to perform this adiabatic driving, and yeah, and they need to ways to tune the temperature of the atomic cloud to hot reservoir to cold reservoir. And in that case, they get much better efficiency. So the efficiency of the machine will be like 0.91, but it means for kind of the losses that they have when they cool and hot the cloud, they get a slower, they get a lower value, but in any case, it's much higher than the other. But the price, of course, is that the power is not so high. Okay, so let me now shift a little bit to the case of continuous operation engines. So those are a different type of engines. They don't have moving parts like in the cycle, but in general, they just are composed by a quantum system that is put in a non-equilibrium steady state, where it has some coupling to reservoirs, but this coupling sticks over time, and the machines are able to perform some thermodynamic tasks in this long time frame. So some examples are this, for example, models of the small absorption refrigerators, which are able to cool a cold reservoir by using one or two heat sources. There are also like this, for example, three-level regulator or three-level amplifier, in which you have access to two reservoirs, and there is some input field that performs work on the system or takes work out. And there's also a plethora of devices like quantum dot emergent investors or other electronic devices that also have contact with different terminals that put a different temperature. And then so you can have quantum dots that are just like qubits in this case, so that you can construct even models like these or others. Here the point is that apart from heat exchange, we can also have particle exchange, so we can have like non-canonical ensembles, we have like more flexibility to implement it. So let's, before just focusing just one example, I will take this example of the three-level laser. So in this case, the working substance, this is the Hamiltonian, as you can see there. So we have these states, 0, 1, and 2. The Hamiltonian will be this thing. So we have some energy spacing between the state 0. So we assume that the energy of the state 0 is 0. The state 1 has EW, and the state 0 has EA. And EA is just EW plus EC. So the idea is that we are going to couple this transition of energy to a hot reservoir. We're going to couple the transition of EC with a cold reservoir. And this transition will be free and will be just driven by an external, for example, laser, no? Just an external field, classical external field. So that will be the bare Hamiltonian of the system. And if we include the external driving, we will add a term that is time dependent and will lose charges. It just generates transitions between state 0 and 1 in a coherent way. Okay. So one can derive a Lindblad-Master equation for this model, assuming that the external driving is free in comparison with the energies of the system, the energy spacing. And we get an equation that looks like this within the rotating frame. Okay, so here the only thing that appears is the part of the driving, but this I put this up to R because it's in the rotating frame. In the rotating frame with respect to W, then what happens is that we eliminate this time dependence. Okay? And then we have the dissipative part. And in the dissipative part, we have this sum here, or the two reservoirs, quote unquote. And then we have two processes for each reservoir. One will be the absorption, and one will be the emission, and this the absorption. Okay, and they can be operated without those dissipators commonly are just like the wind that form, right? Because if we don't have this operator, the system in this way, so that the hot reservoir induces either like emission, which means that we jump from state 2 to state 0 with this rate, right? Or we go up from state 0 to state 2, absorb the photon from the reservoir, and so we ready to dissipate. And essentially the same for the cold bath, but the cold bath just induce consistency in the first one. Right? Is there any question here? The rotating frame means that so where you think about like broad sphere, something like that for this transition, you will see that the state of the system will rotate, right? But if you apply a unitary transformation, but with just a rotation, you will eliminate that rotation, essentially. And that's the equation that's it. Okay. So the idea is that one can calculate the steady state for the system. We just put to zero the Lindblad equation and obtain some state some state 5. So okay, how to obtain this state here? So one way is to solve this as a matrix equation. So we can build a vector with all the populations and coherences of the sea-level system. And so the idea is that we will have like one population of 0, 1, 2, and eventually some coherences here. So what I usually do in order to solve this kind of equations is just to put everything in a vector. So okay, and we can just put the population and the point. Right? And then I can transform the master equation into a set of Pauli equations, or just the component of the density, right? So it will be something like this. So I call it phi stationary state. So we will have a consistent matrix that is given by this Lindblad master equation that says how are related to the entry of the so I call phi the one that verifies this. just to refer to the. So one can calculate this just from the master equation, just taking the averages here and so on, the matrix element. But there is an easy way also to do that, and I would like to show you. So essentially we can, well, the first thing that we can notice is that there will be, so in the steady state, there will be no coherence in the between levels 2 and 0 and 2 and 1, because there is no any source of coherence there. So the only coupling is to reservoir regarding coherence and kill every coherence there in the steady state. So we can get rid of this character. So we know that this will be 0. That is not the case for the other transition because we have this classical phylactery unit, which is a coherent interaction, right? It is a coherent. So we expect to have some coherence in this case. So the way to construct this matrix W here, we can just look at the different levels and see what are the transitions that connect our levels with other levels. So if I start with P0, so the way in which P0 loses probability is just jumping from 0 to 2, right? Using the Hot reservoir. So essentially, we will have here a minus gamma of up. No, it's only that transition that makes me lose probability in this aspect. What are the transitions that introduce some probability in state 0? So, for example, from state 1, I don't have any coupling to the reservoir. So, in principle, I don't have any transition. The coherent one goes apart. So I will have a 0. Then from the state 2 to a state 0, it is possible to go down with this on the reservoir again, so that I will have gamma down up, right? And then the coherent part that goes with this extra. So for that, I only need to calculate this part of the equation. Right? This is the only part that will contribute to the coherences. So that I can easily say that, yes, performing the calculation for this part, that I will get some pi epsilon or minus pi epsilon. Okay, then we go with this. We have done this for the state 0. Then we go with the state 1. If I am in state 1, I can only get out using the cold reservoir and go to up. No, so the only here I will do minus this. The state 0 is not connected to an incoherent transition to this, so that I take here at 0. And then the state 2 is connected to the cold reservoir. So I can go from state 2 to state 1 with this cold, with the cold reservoir going back. And here again, what I have been as this. Next, I go to the state to the level 2. Again, how can I reach level 2? From 0, I can go with the hot bath up. So gamma hot up. From the state 1, I can go with the cold bath up. So gamma up. And if I am in two, I can go out two, either by going down with the cold reservoir or going down with the hot reservoir. So then I put minus, it's the losing probability in this case. Gamma down, dot, gamma down. And since state 2 is not connected to any other state with coherent transitions, I will get anything on it. Finally, I can obtain what are the coefficients for the coherencies. For that, I have to solve this, but as I said before, it's only this part that matters. So it gets easier. And in this case, I have chi epsilon here minus chi epsilon. Here 0. Here minus. Well, this part enters only in that we have some decay of the coherences, which is given by right? 0. That would be that would be the transition matrix for this. So the only difference with respect to the classical case is that now we have these coherences inside. So we enlarge the variables of the system. This makes, so if I can solve this by just putting to zero this equation, and I get some coefficients for the populations and the coordinates. So I have these coordinates in the steady state. So using that, we can calculate everything. So we can calculate the heat current. Okay, there will be this expression here is the trace of the Hamiltonian times the difficulty part of evolution evaluated in the steady state for hot and cold. So what we obtain is very simple. This is just this expression here that you can even deduce from the picture, because so that will have to be multiplied by the okay. And the idea is that how I absorb heat from the hot reservoir. So I absorb heat when I am in high. Sorry, when I am in high zero, when I go up, and I lose heat when I am in high T and I go down. So there should be a minus there. So analogously for the cold one, so I gain heat when I am in phi 1 and I go up, and I lose when I am in phi 2 and I go down. So again, there should be a minus. So here I put the those are the heats that go out, not okay. So and then we can calculate also the power input from the external field. In order to do that, what we need to do is to calculate the derivative of the Hamiltonian, okay, and so and evaluate it in the steady state. But there is a trick, because of course, so with the rotation, so one needs to be careful that the derivative does not commute with the rotating frame. So the idea is that you need to first do the derivative and then go to the rotating frame. Okay? If you do it the other way around, you get another result. So I go through just the general density matrix. Yep. At some time t, and I call pi the steady state one.
Okay.
So the one in the long time unit.
And the difference between the matrix pi and W is,
Sorry?
what is the difference between this matrix and the matrix W?
So that will be the density matrix.
Uh-huh.
the steady state.
Yep.
And this W comes from rewriting all the master equation in terms of rate equation. So this is essentially this matrix, right? It has is 5 by 5 times this order in this way,
Ah, okay.
right? So for the steady state, this is the so essentially I solve this system equation and then I get all this.
Okay, thank you very much.
But in quantum mechanics, they are ordered this way. Okay, and one can also write down the first, well, as I said, you have to first do the derivative of the Hamiltonian in the Schrodinger picture, and then go to the rotating frame and evaluate it using the steady state in the rotating frame that we calculated. So we get something like this. So we can write down the first law in this setup will be just the changing energy of the system will be just the sum of the different input hits and input work. In the steady state, it will be zero because the state will be fixed. So the energy of the state will be fixed. So then we just have this equal to zero. On the other hand, we can go the second law in this case. It will be just the change in the change in von Neumann entropy of the system plus the entropy fluxes to the reverse. Entropy fluxes to the reverse are just one. I read the one Q1 dot and Q2 dot. I directly eliminated the change in entropy of the system itself because it is a steady state, so it will be zero. And the second law will go after this theoretical answer. So this can be indeed derived from a very general way for many systems, from an information theoretical point of view. Yes, QC and QH. Yeah, I'm sorry for the mess with the notation.
Sorry, a question there. In the driving power, you have that it depends on the coherences, right?
Yep.
So it's like if there was exchange between the quantum information that you have outside of the diagonals and mechanical work.
Sorry, say again.
So it's like you were transforming quantum coherences into work.
You are inputting energy. It would be not correct to say that you are changing coherences into work because, I mean, work is energy, coherences are not energy, right? But we are using a coherent source of energy. And this coherent source of energy operates, right? So this Hamiltonian, what this Hamiltonian does to generate coherences. Now they are related, but not exactly correct to say that we are transforming coherence. It's a coherent source of work. In that case, what we are doing is that we are extracting work in this coherent source.
Okay. Yeah, thank you.
Okay, the efficiency is just that expression there, up, that the work output will be minus this work here, divided by the input heat on the whole reservoir. And again, we get this very simple expression, plus 1 minus AC over EH. Okay. This is in general, this is because this model verifies a nice property, which is that every flux of energy in the steady state, so all the energy fluxes in the steady state are proportional to each other. And this is because all the heat just enter So one transition or other transition, but they are not mixed. So what happens is that we have this property. So the W out over PW is equal to the hot heat divided by pH, and is equal to minus the core heat divided by PZ. So this is very fine in the credit, and this is very useful to calculate that. So, as before, depending on the values we choose for these energy gaps, we will get one regime or another for this device. In particular, one can see that the work output is positive, even only if this condition is verified. So, that will be this area here. So here you can see the work output as a function of the hot temperature, one of the hot temperature, and the ratio of the gap in the lower part and the gap on the upper. Okay, and you see that here you have this heat engine regime, while here when you load this inequality to the other side, but again, it's a refrigeration regime as before. So in that case, all the fluxes stay sign, and in that case they will be using like external work and everything that we do. And this is how the work output look like. It's very similar as in the auto cycle we have to before. So we have always a maximum, and then we have some point for the transition between the two regimes. Okay, so what's different from the other thing? Okay, of course, this is a general question, right? So many models of quantum in this are based on quantum effects, in which the dynamics of the system can show quantum effects. So for example, tunneling, or even you may have like two qubits that are entangled, and this can be an engine. But it's not clear when these quantum effects would affect really the performance of the software, right? So the real question is if there is some quantum thermodynamic advantage in this model. And in order to answer this question, there are different approaches. There are people that what they did is to just define a classical analog of the engine you are looking at, and then compare the performance of these two engines. And for example, this has been done in the paper, but what is the problem with that? The problem is that there are many ways in order to define a classical analog, and the results may be very sensible to that. Indeed, in these two papers, so they reach opposite conclusions. Just not because they are wrong, it's just because they use different things to compare with. So it's not very clear how you will define a classical analog in a universal way. So what one can do is another. What one can do is to use some to state some inequalities or equalities that are verified in the classical case, and try to see if they are broken. So one example is the thermodynamic uncertainty relation. So the thermodynamic uncertainty relation is model independent and is verified for every Markovian system, so that if my system, which is also Markovian, breaks that means that there is some quantum thing. And not only that, but a quantum thing that affects the performance. And this is the thermodynamic uncertainty relation. So what it does is to relate the variance on the average of fluxes, for example, energy fluxes, with the entropy production rate. So the quantity that we have seen before that expresses second law on the set. If you apply this for example, the work, you will have some constraint between the efficiency of the engine, the average output work, and the fluctuations in that work. And in general, what we do is something like this, right? We just arrange terms there and we use that choose and arrange the workout. So that any classical Markovian engine needs to have this ratio greater or equal than 2. But there has been calculations in this model that I show you that says that for some regional parameters, this is this can go, this can be lower than 2. Right? So there are violations of this thermodynamic uncertainty relation in this model. And this is just because we are using this laser, this external field that is generating coherence inside the system. And these violations are a quantum thermodynamic advantage. Why are a quantum thermodynamic advantage? Because you can have either higher efficiency for a fixed level of fluctuation and a fixed work output, or you can either have a higher work output for a fixed efficiency and a fixed level of fluctuation, or you can either have lower fluctuation for a fixed output power and fixed efficiency. And this is what this violation of the theory is. So in that case, we do have a quantum thermodynamic advantage, which is unambiguous. Okay, this model of three-level systems has been also implemented in the laboratory, and we set up with independent. So essentially, what they do is to obtain an effective three-level system like here, and then they have this microwave field that drives this transistor here, which is the one that is used to perform or instruct work. And this work was focused on trying to demonstrate a quantum signature, and they did that, but I have to, that the work was performed before all the stuff of the QR, and in that this what they call this quantum signatures in reality are just obtained using one of these methods of defining a classical analog. So are a little bit ambiguous, I would say. Are not clear. However, I think there is no experiment up to now that has checked this experimentally, this unambiguous quantum. Okay, so this is all I wanted to tell you. So thank you very much. And if you have some questions, I will just have to tell you. So.
It's just a detail I missed in the first system, so in the auto cycle. Yes. So they are using gravity, or why do they have these plates in not parallel but in an angle?
Oh,
Huh?
it's because this is the way to get this force dependency, so that this force dependent on temperature. So because essentially with this stuff for geometry, they can have this field here, so it's asymmetric, so that it can just push up or down the calcium ion.
Okay.
I think otherwise you will have something symmetric there, and you will not be able to move it in the two direction. The two directions is
Okay. I see. Thank you.
Can you go to the slide where you show the driving, please? The coherent driving? Yeah, that's right. Is there any relationship between the coherence of the driving and the work output?
Yeah. So I mean, if you calculate it, this is what you say, right? So this comes from let's say, applying this term to the state five, which is what this does is to select this system. But if you don't have this driving, you will not have here from a steady state model. That is the point. If you only have interior position, you will have everything zero and only population. So it will become classical. Okay. Completely classical.
So you're doing like control in some sense?
Well, not at all, because this is just it's a periodic driving. And just put it there. And just because of how you split the energy gap, you will have one regime or the other. But in principle, you don't need to change things on the line, right? You just prepare your system, plug the laser, define the fluid path, and you just let it go. You just wait until it reaches the steady state, and then it will go.
So in the quantum auto engine case, it seems like by design, you're moving in between equilibrium states, right? And these states are typically always diagonal in the energy basis. So there it's maybe hard to see how coherences may be playing a role in the thermodynamic behavior of the system, right?
Yeah.
Is it possible to design these kind of cyclic engines moving in between the states with quantum coherences?
Yes, there has been some cases. One case that I studied, for example, is to change this reservoir by a reservoir which is not only at a higher temperature than the other, but it's also squeezed. So you have like segregation squeezing. And in that case, you profit from the fact that if you put something in contact with a squeeze bar, this state will get squeezed as well. So that this flow will be the same, but after contact with the squeeze bar, the state in C will be squeezed. So it will have coherence. And then you can adapt the flow here in order to get advantage of that coherence. So you can transform back this, you can extract work by changing this coherence, so that eliminating this coherence. Okay. And then in that case, you get some advantage in the power.
Thanks for the talk.